the screen is yours.
Okay, so I want to thank everybody that organized this event. It's a pleasure and very nice of you to come and show up. This talk will be about the regularity of the min-max of Blackwell-Borel games. This is something that Eran already mentioned yesterday. It's about the approximation and with the closed set and open sets, and I will go into the details soon. And mainly, I will emphasize how we can apply this thing that we refer to as regularity to get equilibrium existence result and characterization of the set of equilibrium payoffs results. Sometimes we refer to this as Folk theorems. And this is the first out of 3 results that are all part of an ongoing project of researching this topic, altogether with Janusz Flesch and Arkady Pentuchinsky from Maastricht University and Eilon Solan from Tel Aviv University. So, okay. Please do not hesitate to interrupt and ask questions. I can only see part of your view in the screen, and I don't think I can see the, oh, I can see the chat. Okay, I probably can see the chat, but better if you just speak up. You saw already several results that enable me to put the current work in context. So Ron Peretz dedicated one slide in his talk to tell us about, is there a question already? No? Okay. Ron Peretz dedicated one slide in his talk to tell us about Gale and Stewart result from 53. They considered zero-sum games with alternating moves and with winning sets. That is, there is a set W, player 1 wins if the infinite play is in this set, and player 2 wins otherwise. And they proved that if the winning set of player 1 is either open or closed, then the game is determined, meaning either there is a winning strategy for player 1 or there is a winning strategy for player 2. Ron also told you about the work of Martin from 75, saying that such games, meaning zero-sum, alternating moves with winning sets, such games are determined for all winning sets that are Borel measurable. So not necessarily open or closed, anything Borel measurable. Then Janusz told us about the work of Mertens and Neyman. This work goes beyond zero-sum and winning sets. So the question was no longer whether the game is determined, meaning whether a player can necessarily win the game, but whether there is an equilibrium or an epsilon equilibrium. Finally, one told us in his second talk about the work of Martin from 98, showing that in zero-sum simultaneous move games, so now the players are allowed to move simultaneously, a value exists. So a value is the equilibrium payoff when the game is zero-sum, so an equilibrium exists, a value exists. Our work will deal with multiplayer non-zero-sum games, so like Mertens and Neyman, but simultaneous moves, when the players move simultaneously. So it's different than from the models I just described. Here is the talk outline, what I'm going to say. The main result that we have concerns game with tail measurability, meaning either winning sets that are tail measurable or payoff functions that are tail measurable. So first thing I'm going to do is tell you what tail measurability actually is. Then I will be able to state the results that we're having. I shall remind you quickly about the equilibria and epsilon equilibria, exactly what it is. And then we discuss a little bit properties of the min-max. Specifically, afterwards, we'll talk about regularity of the min-max. This is the approximation thing that, again, Eran already mentioned yesterday. And then how to use the regularity of the min-max for showing equilibrium existence in games with tail-measurable sets and tail-measurable payoffs, and to characterize a set of equilibrium payoffs. Sometimes we call this a full theorem. So this is the general plan. And again, please interrupt me if anything is not sufficiently clear. Think about infinite horizon games with winning sets. With many players, each player has a winning set such that her payoff is the characteristic function of this set. So 1 if the play is inside this set, and 0 otherwise. Specifically, we are interested in tail-measurable sets. So when is a set of plays tail-measurable? When the membership of a play in the set does not change when we change the actions played in finitely many periods. In other words, we have 2 plays here. I hope you can see my cursor. Yes, you can. Okay, so this is one play, P, A1, A2, and so on. And here are K action profiles, B1, B2, up to BK. Q is tail measurable if for every play that belongs to Q, if we replace the first K action profiles with any K action profiles, here B1 to BK, then the resulting play still belongs to Q. So replacing a finite number of action profiles does not affect the membership of this play in the set. In other words, if 2 plays coincide from a certain period on, and one of them belongs to W, it belongs to the winning set, here Q, then the other one belongs to the tail set as well.
I have a question.
Yeah.
I have a question. I have the impression that there must be other names for this concept. It's like prefix free or something of that sort.
Maybe. I'm not aware of other names, but my guess would be that you're right.
Yeah. Prefix independence, I think you mean, right?
Prefix independent? Maybe.
I think with prefix independence, you don't need to respect the length when you replace, so you can something shorter, or you can just prepend something. So if it's true word, then where prefix you would replace it would still true. It don't need to that the replacement as long as the object that you replace.
Okay.
So there is something in your definition that is more active and that is specific. I haven't seen it in the way before.
Okay, I know it's related to something that is called, I believe, shift invariance, but this is slightly different. It's not the same. Yeah. Shift invariance, you can think of tail sets that are not shift invariant. So here are examples of tail measurable sets. The set of plays in which some player I plays a certain action AI infinitely often. The set of plays in which a certain action profile is played with lim sup frequency of, say, at most half. The set of plays in which a certain action profile is played at most finitely many times at even periods without any specific condition on the odd period. So you can see that this is not shift invariant. Okay, if we shift it one, then we change the membership, okay, because of the odd and even. So these are tail measurable sets, and tail measurable sets of plays form a sigma algebra that is different than the Borel sigma algebra. We also discuss tail measurable payoff functions. So what are these? When is a payoff function tail measurable? So given a play, whenever we change the action profiles in finitely many periods, we get the same payoff as in the original play. So the same idea behind it. Take some play P, A1, A2, and so on, replace K action profiles. If the function G is tail measurable, then it will assign the same value to the 2 plays, the one before the replacement or after the replacement. Again, if 2 plays coincide from a certain period on, then the function assigns the same value to them. More formally, a function is called tail measurable if for every real number, the set of plays whose payoffs are at least that number is a tail set. examples for tail-measurable functions. So suppose that we have some per period payoff. So for every 1 period action profile, there is a function that gives us a real number that we can think of as the payoff of player I for this action profile, okay? The numbers represent the payoff. So we have an infinite stream of payoffs, and we need to determine how the player evaluates an infinite stream of payoffs. So here are some evaluations that are tail measurable. If we consider, for example, the lim sup of the averages of these payoffs, then we get a tail measurable set. If we simply think of the lim inf of the payoffs, then it is tail measurable. If we take sum of two tail measurable functions, then we end up with a tail measurable function. However, the sometimes popular discounted sum is not tail measurable, okay? Because it's not true that you can replace a finite number of action profiles and still get the same payoff. There are also classical computer science evaluation criteria, Buki, Kobuki, I'm sorry if I'm mispronouncing the names, parity, Muller, and street objectives that are tail measurable, though these objectives would usually be defined for graph games and expressed using state spaces. They all have natural analogous in the setup of Blackwell games. So now that we know what are tail measurable sets and what are tail measurable functions, I can state the results. So we consider non-zero sum simultaneous move games with tail measurable payoffs. The number of players doesn't need to be 2, it can be larger than that. And I will emphasize 2 results. One result of existence, any simultaneous move Borel game with finite number of players, finite action sets, and bounded tail measurable payoff functions admits an epsilon equilibrium for every epsilon, and also a characterization result. And I will give you the exact characterization when we get there. So a characterization of the set of limits of epsilon equilibrium payoffs as epsilon goes to 0. So this is going to be the results. I know you already heard that, so I'm going to be quick just to remind you in case it's very early in the morning and you are still half asleep. So what's an equilibrium and what's an epsilon equilibrium? Well, first, what is a game? So we have the set of players, we denote it by I. Each player has his or her set of actions and his or her payoff function. An equilibrium, a vector of strategies, one strategy for each player, such that a single player deviating to a different strategy, playing a different strategy than the one assigned to him by the vector of strategies in the equilibrium, while all other players still conform to their equilibrium strategy, well, such a behavior is not profitable. Okay, you cannot gain by unilateral deviations. And an epsilon equilibrium is basically the same, only we say that the player cannot gain more than epsilon by unilaterally deviating. And there is an example of why we need epsilon equilibrium, but I think you already saw some examples in the previous talks of games where there is no equilibrium, but there are epsilon equilibrium. If there is some demand from the public, we can go through another example, but if not, we can move forward as you wish. So sometimes we don't have an exact equilibrium, but we have epsilon equilibrium for every epsilon, and this is why it's sometimes useful. The min-max.
Galit, I think in the chat there was a wish to show such an example.
Oh, yeah. Okay, sorry. I don't see the chat very well.
Yeah, that's why I'm jumping in.
Okay, so why epsilon equilibrium? Good question. I have just the answer for that. So here is an example of a game that does not have exact equilibrium, but has an epsilon equilibrium. So think of a game with one player that has 2 actions, and he can. They are called A and B, And this is period 1. And if he chooses action A in period 1, his payoff is 0. And if he and the game ends. And if he chooses B, then we move forward to period 2. And in period 2, again, he gets to choose between action A and action B. And if he chooses A on period 2, he gets a payoff of half. And if he chooses B, then the game goes on. Period 3 is again between A and B. If he chooses A, then he gets a payoff of 2/3. And if he chooses B, then the game goes on. And I think by now you understand it. The payoff depends on the first time that you choose action A after some finite stream of B's. But if you choose B forever, okay, generally speaking, if you choose A after period T, at period T, then your payoff is 1 minus 1 minus T. But if you choose B forever, then you get a payoff of 0. So of course you can get as close to 1 as you wish. You just choose B many times, okay, enough for a long enough number of times, and then you choose A. So you can approximate the payoff of 1 as closely as you wish, but there is no strategy that gives you exactly 1. So there is nothing that is an exact equilibrium, even for the player with himself. Oh, I can see there are many things on the chat. Okay, just let me know if there is something that I need to refer to in the chat. So this is an example of a game that has only epsilon equilibrium and no exact equilibrium. Okay, no equilibrium exists. Epsilon equilibria, however, does. And that doesn't go back to where we are. So oh, and now you get a preview. Now you know all the answers. Sorry, it was supposed to get me back, but now it's stuck. Okay, now we're back. Sorry for that. So the min-max. Let's discuss the min-max. The min-max value of a player in non-zero-sum game is basically the payoff that a player can defend knowing the strategies of the opponent. Similarly to a game with 2 players. Specifically, if the game is a game with winning sets, then we're discussing the min-max of the probability to get into the winning set. So generally speaking, it's the best that a player can defend to get given her payoff function. And specifically with winning sets, it's the best probability that she can get to get into the winning set. So the min-max is going to be the main tool that we use to prove the existence and to prove the Folk theorem. First thing I'm going to tell you is that the min-max is not always so well behaved. Okay, this is what I wanted. The min-max is monotone. Sorry, it's just jumping here. Okay, I think I fixed it. Let's see. I think I fixed it. Okay, my mouse is jumping around. The min-max is monotone in the following sense. If we're looking at the min-max of a sequence of increasing sets, then this min-max is non-decreasing. Okay, an increasing sequence of sets, the min-max is non-decreasing. However, it's not continuous in the following sense. There exists an increasing sequence of Borel sets. C1 is a subset of C2, is a subset of C3, and so on, such that when Cj is the winning set of player 1, the min-max of the limit set is not equal to the limit set of the min-max. We denote the min-max by V, by small v. Okay. To convince you of that, I will show you an example. So consider a game with 2 players, player 1 and player 2, a zero-sum game. The winning set of player 1 depends only on the actions of player 2. And player 2 has 2 actions in each period, A and B. And now we begin to define an increasing sequence of winning sets. So the first set that we define is B0, and it consists of two plays, the play of playing infinitely many times A, and the one where we play infinitely many times B. BK is a set of plays that begins with all the plays that begin with playing K times action A and then action B. CJ, now we define the increasing sequence of winning sets, is the union of all the B's from K equals 0 to K equals J. What does it mean? It's the set of plays, CJ is the set of plays such that it's either always A, or always B, or K times A followed by B and then continues however, okay? Now let's think about the min-max of these CJs. So if we think of a finite J, 100, 500, okay, any finite J, it's clear that player 2 can avoid getting into this CJ. All he needs to do is to play J plus 1 times A and then B and then whatever, and then we're out of CJ. So for every finite J, the min-max of CJ is 0. Therefore, when we take the limit, it is still 0. On the other hand, if we look at the limit set of CJ when J goes to infinity, this is simply all the plays, because each and every play you can think about is either all A or all B, or begins with some number of A's followed by B. And therefore, the value of the limit is 1. So the limit of the values is not equal to the value of the limit. It needs to be not equal. So it's not always well behaved. It still has an attribute, again, that was mentioned yesterday, that we will heavily use, sometimes something that we call regularity. From probability theory, we know that the probability measure is a regular operator. This means that given a probability measure and a set W, under conditions that are not too restrictive, the probability of a set is equal to the supermum of the probabilities of closed subsets of that set. This is sometimes called inner regularity, and also equal to the infimum of the probabilities of open supersets of W. This is sometimes called outer regularity. And it turns out that similar attributes hold for the min-max. And yeah, I got my mouse to work. So similar attributes work for the min-max. Again, as Eran mentioned yesterday, Martin in 98 and Mitra, Sadet, and Perves in 92 proved the regularity of the min-max in the case of 2 players. We generalize it to more than 2 players. And the proof method is similar to Martin and similar in other aspects to Mitra, Sadet, and Perv. We use an auxiliary alternating move games where player 1, you saw this method already, tries to prove that a value can be obtained. Player 2 tries to prove him wrong, or player 1 wrong. So similar methods, slight alternation, and the proof works for more than 2 players. And this is the thing that we will use, that we will employ to get existence of equilibrium and to get the characterization of the set of equilibrium payoffs. So now for the proof. Existence of equilibrium for games with tail-measurable winning sets. One remark, for the regularity result that I just mentioned, the number of actions can be countable. However, for the applications for game with tail-measurable sets of payoffs, we assume that the number of actions available for each player is finite. Okay, and I will tell you if you want exactly where we use this finiteness assumption, because it's important. So we have a number of players. Each one of them has a winning set, Wi for player I, and this winning set is assumed to be tail-measurable. I will tell you exactly when we use attributes of tail measurability, when we use the implications of tail measurability, what does it imply? Why do we assume that? But for now, each player has a winning set that is tail measurable, and we try to generate an equilibrium. The key to generate an equilibrium here is to find a play path such that the payoff is at least as high as the min-max for each one of the players. So the winning set of player I is Wi, and here is the first implication of the assumption that the plays are tail measurable. I claim that the min-max of this Wi is either 0 or 1. Moreover, it is either 0 after any history or 1 after any history. To get some intuition as to why it is either 0 or 1, let's entertain the thought that it is 1/2. Then a player has a strategy that guarantees that she gets into the winning set with probability half. From Levy's 0-1 law, there is some period t far enough along the play such that with probability close to half, at period t, the player knows that she wins almost for certain, that she is winning inside the winning set, and with probability half, she knows almost for certain that she is lost, that she is outside of the set. But the set is tail. So this finite t, when this realization comes along, it doesn't matter, okay? She can restart this strategy and get another probability half in case she finds out that she is lost. She gets another chance, another probability of 1/2 to enter the winning set. So I hope this convinces you that if she has a probability of half, then she has a probability half plus half times half, and then so on and so forth. So she can have infinitely many opportunities to get into the winning set. And therefore, if she has a probability of half, she has a probability of 1, basically. So it's either 0 or 1, the min-max. And we want to play where each player gets at least their min-max value. For the players whose min-max is 0, this is not a challenge, right? Any play gives them their min-max value, which is 0. That's not a problem. So we can assume, we can just, for now, disregard these players, we ignore them, and we assume that all players have a min-max value of 1. Okay, so now we want to find a play that is in the intersection of all the Wi's, okay, of all the players, because we assume everybody has a min-max value of 1. So now we use the inner regularity. We approximate the winning set Wi with a closed set Ci such that the min-max of the closed set is 1 minus epsilon. Next, we define a set, CIM, the set of plays where after m periods, there exists some continuation that is in Ci, some continuation. Player I is not totally lost, comes period n. Observe that this is a superset of Ci because you just need some continuation to be inside. So Ci is a subset of CIM. So remember this set, CIM, the set of plays where after m periods, there is a continuation that is in Ci. Ci is the closed inner approximation of Wi. Yeah, okay, we move on. Now we define the set Cm, which is the intersection over all the players of CIM. So this is basically the set of plays where after m periods, all players are still alive, okay? In the sense that all players still has continuation payoff, the continuation of the play, each one in his respective CI. Okay, so
Galit, can I ask to understand this set CIM? Because I'm confused.
Yes, please.
Does it mean that, so when you say that after M you can get into the C, does it mean, so the set Cs might not be tail measurable, right? They are not.
Yeah.
Right. So this is the first step to understand. Then you say, well, if I play a way so that the play that I play, if I replace the first M steps, then I'm in C. Is that the way you mean it?
Again, I'm not sure I understand.
Okay, are you saying there is a play such that when I throw away what happened in the first M steps and then replace it by the right thing, and I put it together with what happens after stage M, I get a play that is in the set C?
I think it's not accurate. What I mean is this: the set of plays such that when you look at the first M periods, there is some continuation of this first M period that is still in CI.
Okay. So
you find a way to continue it that keeps you in CI. Now, note that we have I players. Maybe each one of them have a different continuation that keeps them in their own CI. Okay, but each player needs to.
Okay, that's the trick. Okay.
Each player needs to have some continuation, something, some possible future when he's not lost.
Okay, so basically, if that player could choose alone what happens, it could make sure to be in C.
Yeah, exactly. If that player was free to choose the entire
it's not yet completely excluded. Okay. Now I understood. Sorry for the question.
No, thank you for the questions. Please, people, ask questions. Yes, so CM is the set of plays where at period M, we don't have a player that is completely lost, that is outside, that has no possible future in his CI. Okay, this is the set CM. Now, let's think about the set CM. Let's think of a finite game, a game of M periods, where each player tries to get into the set CIM. Okay, so this is a finite game. And in a finite game, here we use the assumption, by the way, that the set of actions is finite. In a finite game, we know that there exists an equilibrium. And moreover, we know that in equilibrium, each player gets at least her minmax value. We're going to use this. Okay, we're going to use this. So each player gets at least VI of CIM in the finite game that has an equilibrium. Using the equilibrium strategy, a player gets at least VI of CIM. Remember that CI is a subset of CIM, okay? CIM is just all the beginnings. CI is more restrictive. And we know that the value of CI, the min-max of CI is 1 minus epsilon. So in the finite game, the one that ends after M periods, and when each player just wants to get into CIM, the min-max of each player is at least 1 minus epsilon. And since this is an equilibrium, and since in equilibrium, each player gets at least their min-max value, it means that when all players play their equilibrium strategies in the finite game, each one of them enters their CIM with probability at least 1 minus epsilon. Okay, so each player, using equilibrium strategy in the finite game, each player enters CIM with probability at least 1 minus epsilon. So consider the probability induced by this equilibrium strategy in the finite game. We have here I events, each one happening with probability at least 1 minus epsilon. For epsilon small enough, this means that these events need to have an intersection. Okay, their intersection is not empty. Therefore, we conclude that CM is not empty. Okay, this was a little bit of a lengthy explanation. So if some clarifications are needed, please ask. Okay.
Sorry, I have a question. Yeah. Probably I didn't quite understood the definition of CIM. Okay. So for me, maybe I restate what you explained to us, that you spot what is confusing to me. So as understood, if in the set Ci there is any play, because the set Ci is supposed to be tail measurable, then if I look at any run there and I look at the first M part of it, the first M action, and change it to anything, then I will stay in the set.
No, wait. First, the set Wi is tail measurable. The set Ci is not tail measurable.
Okay, I think that's
tail measurable. So, so this is the first point that maybe I was not very clear about. So Ci is not tail measurable. It's an approximation from the inside with a closed set of a tail measurable set, but it doesn't need to be tail measurable by itself.
Okay, thank you.
It most probably isn't. Still, I want to explain some more what is the set CIM, because if it's confusing, then it deserves a better explanation. So the set CIM, so okay, there is Wi, which is the winning set of player I. There is Ci, which is the inner approximation with closed set of the set Wi. Now, suppose we stop the game after M periods and we ask the players who still has a chance to get into Ci, okay? If player I says, I still have some continuation that allows me to get into Ci, if I'm able to choose the continuation, I can guarantee that I can get into Ci. I'm not completely lost. There is still some future where I see myself in Ci. If this is true, then we are still in CIM. CIM are all the beginnings of M periods beginnings where player I can still get into CIM, where there is some continuation that leads us into CIM. When we look into the set CM, which is the intersection of all CIMs, it means that for all the players still have some future when they are still each one in their respective CI. It doesn't need to be the same future for all the players, but each player needs to have a future that guarantees that he is still inside CI. So this is CIM. And when we look at this is CM, sorry. When we look at CM, we can use the fact that CM can be, you can try to get into CM using a finite game to say that it needs to be not empty. It cannot be empty, because if each player can have a probability of at least 1 minus epsilon to get into CIM, when they all use the equilibrium in the finite game, then these events have a non-empty intersection. So there has to be some play in this intersection, in this CM. Are there more questions?
Galit, can you show an example where, I think related to the previous question, but for this explanation, where CI cannot be chosen to be tail measurable?
Where CI cannot be chosen to be
tail measurable.
Cannot be.
CI is closed. CI is closed. I mean, there are only two tail measurable closed sets: the empty set and the
everything.
thing.
Yes, the empty set and everything. So actually, everything that is not, thank you, Arkady, everything that is not the empty set of, or everything cannot have an inside approximation that is tail. Yes.
Thank you for the example, because now it quite make a lot of sense, because the only times that, in fact, if the winning set was everything, then actually everything would trivially also hold. And that was a very good example. Thank you.
Thank you. Okay. So I hope it's clear now that CM is not empty. Now I remind you our mission. We began with a mission. We wanted to find a play that is in the intersection of all the WIs, and we will find a play that is in the intersection of all the CIs. But so far, all we have is that the intersection of CIMs is not empty. So we still need one step to go. So we're done. Now we increase the M. We look at Cm, Cm plus 1, Cm plus 2, and so on. Observe that Cm plus 1 is a subset of Cm, okay? Because it's easier to still have a future that keeps you inside Ci when you're looking at M periods than when you're looking at M plus 1 periods. There are more requirements here. So we have nested non-empty compact set. Oh, sorry, my computer is making problems today. It chose today to make problems. So we have nested non-empty compact sets. And from Cantor intersection theorem, we know that this intersection, the intersection of all CMs, M from 1 to infinity, is not empty. And this intersection is exactly the set of plays where all players win. All players, the plays are all in Ci for all i's, okay? Because every player has a future that is inside after 1 period, 2 periods, and up to infinity. So this intersection is not empty, and therefore we can find a play that is inside all the Ci's. Ci's are inner approximations of Wi's, so we just found a play that is in all the Wi's. This enables us to build an equilibrium. How is the equilibrium working? The players play some play that is inside this intersection when all players win. Now, I remind you that we disregarded the players that had a value of 0 because we said, well, they get at least 0 anyhow, but now we need to consider them as well. So every player that had a min-max value of 1, they get at least 1. They have no profitable deviations. They get their maximal payoff anyhow, so no deviation. The players that had a min-max value of 0, well, we never established what is it that they get. Maybe they get a 0, maybe they have 1, and they possibly have profitable deviation. And the equilibrium instructs that if a player deviates from this play path, then her opponents sanction her, punish her by playing the strategy that gives the deviator the min-max value. Now again, the payoff is tail, okay? The set is tail. So by deviating once, you cannot enter your winning set, okay? And you can always be punished down to your min-max level after any finite period. So this punishment is effective regardless of when it was initiated. So for the players who got 1, they have no profitable deviations. For the players whose min-max value is 0, if they deviate, they get punished. So this is an equilibrium. We use here another attribute of tail measurability, that the min-max doesn't change, and that deviating once, you cannot alter your payoff in a way that you have some positive gain. So this is the existence of equilibrium for games with tail measurable winning sets. Now we move forward. Unless you have questions, again, please feel free.
Yeah, I have a question. Is the chance, this is not subgame perfect, right? Because it might not be in the interest of the other players to punish deviator, right?
Correct.
Is there a way of, spicing it up that, they don't need to, I mean, I haven't thought about this ever. Maybe they just need to punish for finally many periods or something to make sure that that guy doesn't get into his good set, and then they can go back to, to basically the set C. I mean, just changing the beginning or something.
I see your concern, but nothing that you can do during finitely many periods has any effect, right? So
yeah, so there's no way of punishing that guy, right? And getting back and still getting the good payoff for you.
Yeah, you can say that we're going to do something and then we're going to restart, but then it's not clear what's going to be the payoff if he keeps deviating, for example.
Yes. Okay, so because in repeated games with
Yeah, I know.
with discounting and so on, you can do things like this, right? You can
sometimes, yes, I
you
know.
can punish the other guy, but then you go back to what you like. And
I
here
admit,
there's no chance, right?
yeah, I admit it's a tempting thought because there are proper sub games here. Everybody knows everything. It's tempting to think of sub game perfection, but actually nothing that you do in a finite number of periods affects anything. So it's not clear.
So basically, it should actually be possible to find counterexamples where cannot have a subgame perfect equilibrium.
That's an interesting thought. I never thought of that, but it's an
that would make your paper even stronger if you find a game with such an example. That would be a good thing, I think.
Yeah, thank you for this comment. It's an interesting idea. Yeah, thanks.
Okay, sorry. Interrupting. Okay.
Okay, so this was existence of equilibrium with tail-measurable winning sets. Now let's move to tail-measurable payoffs if my mouse will allow me to move. Yes, it did. Okay.
Sorry, I have a question.
Yeah.
In the previous slide, so if there is a deviation, because the intersection of the CM may not be tail-measurable, we may get out of, if one of the player, the one that has a payoff 0 does a deviation, we may get out of CM as this intersection, but of course still be in W, yes? So how are we sure that still all the players that were supposed to get 1, they will get 1? Because I don't know if my question is...
Yeah, I think I understand. I will try to answer, but if I'm not answering, tell me. Okay, so you are right that the intersection of CM is, I don't know if it's, the intersection of CM is the set of plays that are in the intersection of winning sets. Winning sets are tail, finite intersection of tails. I think it is tail, but people correct me if I'm wrong. But even if it's not, the equilibrium construction is about playing a pure play path. So we select 1 and it's pure. So you know exactly what everybody is supposed to be playing at each period, okay? And they're supposed to be playing that, and if somebody deviates, then they're punishing him, and that's it. They punish him till the end of times. Okay, so after they punish him, there is no after. Okay, they don't go back to anything like traditionally they sometimes do in repeated games, that you punish for some number of and then you go back. That's not the case here. You just punish him forever. Is this answering your question?
Yes, it does.
Okay.
And I think you might be also right that maybe this set is already tail because...
I think it is tail.
Because,
yes, it is the intersection of finitely many tail sets. So, yes. Okay. But again, it just relies, but again, it just relies on playing a pure play. Okay. So now we move to tail-measurable payoff functions. So we move from payoff function that is a characteristic function of some tail set to any tail-measurable payoff function. We use similar methods to show that there is a play whose payoff is, for each player, is at least their min-max minus epsilon. So the ideas are very much the same. First, we define for every player the set qi epsilon of his payoff, which is the set of plays where this player gets at least their value minus epsilon, their min-max minus epsilon. This set is tail. And again, we go to the implications of tail measurability. The min-max value is the same for all subgames, meaning no finite history matters to what is the min-max of the game. Okay, so and because this set is tail set, the probability of getting into that set, the min-max probability of getting into that set is either 1 or 0. The min-max of that set, if we consider it to be the winning set, is either 1 or 0. But because this is the min-max minus epsilon, the player can guarantee this payoff, so it has to be 1. So the min-max of this set is 1, and then we can employ similar reasonings that we had before to show that there is a play that is in the intersection of all these qi epsilons for every epsilon. So this is basically repeating the same technique. And again, the equilibrium, you pick one such play and we play it forever or until a player deviates. And if a player deviates, and he's being punished forever with his min-max. And this is and 2 epsilon equilibrium. So this is just generalization of the payoff function that is the characteristic function of a tail set. Okay, so this is for existence of equilibrium and epsilon equilibrium. Now we move to characterization of the payoffs that we can obtain in equilibrium. The term fault theorem in game theory refers to a theorem that characterizes the set of equilibrium payoffs, usually within a repeated game framework. In this setting, since sometimes you already saw epsilon equilibrium does not exist, we focus, exact equilibrium does not exist, we focus on epsilon equilibrium. And we ask what is the set of payoffs that are the limits of epsilon equilibrium payoffs as epsilon goes to 0. What's the limit set? What's the set of payoffs that can be approximated with epsilon equilibrium payoffs for decreasing epsilons? To better understand what we mean by that, let's consider an example and try to characterize the set of equilibrium payoffs in the example. So we have a sympathetic game of 2 players, player 1 and player 2. Player 1 has 3 actions, top, middle, and bottom. Player 2 has 3 actions, left, center, and right. And we have a small notation for an action profile A1, A2, and a number n. We denote hashtag A1, A2, n to be the number of times the action profile A1, A2 was played during the first n periods. So you can kind of guess it's going to depend on frequency of using different action profiles. And these are the details of the payoffs. If the lim-in frequency, okay, the lim-in frequency of the 2 action profiles combined, TL and MC together, is above half, then the payoff is 1-1. So if they manage to play these action profiles, these 2 action profiles here, the sum of their frequencies with a lim-in of at least half, then they end up each gaining 1. If the lim-in of the frequency of BL is 1, then the payoff is 4-1. Now I'm going to put it in the matrix, and I'm asking you not to be confused, because usually when we put payoffs in matrix, we refer to per period payoffs, but that's not the case here. I just couldn't find a better graphical way to help you realize what's going on. So be aware, it's not per period. This is what you get if the limit of playing this set is, for the frequency of playing this cell is 1. And similarly here, -1, 4, if the limit of the frequency of playing this is 1. For all other things, the payoff is 0. So 0, 0, 0, 0 everywhere else, or in cases that we don't reach these frequencies and play all over the place. Now, let's take a look at this matrix. Observe that if player 1 plays forever B, okay, B, 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 then the maximum player 1 can get is 0. And this is the min-max of player 2. Okay, so this is the min-max action of player 1. This is when player 1 is min-maxing player 2, and the min-max payoff is 0. Similarly, you can see it's symmetric. So similarly, if player 2 is playing R, then the best that player 1 can do is 0, and this is the min-max. So we know the game, it has 4 possible payoffs, okay, 4 possible realizations of payoffs. We know what is the min-max. Now, what is the fault theorem here? What can the players actually obtain in equilibrium? Okay, so it's clear, or I think it's clear, that the players can coordinate on getting the 1-1. say they decide to play almost half of the time TL, and I don't know, some of the time CN. Okay, they can coordinate on that, and suppose that if somebody deviates, is punished by the min-max. So 1-1 is obtainable through an equilibrium. 0-0 is also easy to obtain. If both players min-max each other forever, nobody has a profitable deviation, you get 0-0. So we can get 1-1, and we can get 0-0. This much we know for now. Furthermore, there is a paper by Solan and Solan that tells us that the players can use the first periods of the play to conduct joint lotteries. Now, I won't go into the details of joint lotteries. If somebody is interested, you can share the link to this interesting paper. Joint lotteries use the randomizations that the players perform over their actions to generate any distribution over outcomes in such a way that no single player can affect the result by deviating and altering his own actions. So for now, we just use it as a black box. We can assume that the players can together randomize over whatever they want. So it's clear that they can randomize between 0-0 and 1-1 and get any distribution of 0-0. So in expectancy, they can get any payoff between 0-0 and 1-1. Let's take a look at a graph. Okay, so here are the payoffs, the possible payoffs of this game. We have 0-0 here. We have 1-1 here. We have 4-1 here and -1-4 here. So far, our analysis told us the following thing. The players can get 0-0 here. The players can get 1-1 here. The players can get joint randomizations to get all this segment connecting 1-1 and 0-0. Fine. What about the other payoffs? For example, it's very tempting, especially if you're familiar with folk theorems in repeated games, it's very tempting to think, what about randomizing with probability half this and half this? You get 1/2 in expectation. That's way better than 1-1 and 0-0, okay? Can we do that? Can we do that? No, we cannot do that. We cannot do that because indeed we can randomize between -1, 4, and 4-1. But if the realization of this randomization is going to be, for example, 4-1, then player 2 will have a profitable deviation. -1 is below their payoff function, below their min-max. So we cannot obtain it. So if we look at, they can randomize over different payoffs, so we can consider convex hull of payoffs. But if we try to consider the convex hull of feasible payoffs, that's the dashed line here, and see which part of it is above the min-max level, that's the yellow triangle here. We cannot get that yellow triangle as much as we want, because this means putting some positive weight, some positive probability on plays where if these are the realized plays, then a player has a profitable deviation, okay? We cannot place any probability on plays that give us 4-1 or -1-4. So out of all these feasible payoffs, all we can obtain is this segment, connecting 0-0 and 1-1. So here is a generalization of this theorem. So here we had a finite number of payoffs. So we didn't need epsilons, but generally speaking, I remind you of the set QI epsilon, which is the set of plays that give player I at least their min-max minus epsilon. So let's think of this set here. For player 1, it's the set of plays that give him at least 0. Where does player 1 get at least 0? 0-0, 1-1, and -1-4. These 3 points are in Q1 epsilon for epsilon small enough. What is it for player 2? 0-0, 1-1. Player 2 needs to get at least 0. So 0-0, 1-1, and 4. sorry, I confused you. Before it was 0, 0, 1, 1 and 4 minus 1. This is for player 1. And now for player 2, 0, 0, 1, 1 and minus 1, 4. Q epsilon F is the intersection. So in the intersection only leaves us with 0, 0 and 1, 1. These are the two payoffs that, the two feasible payoffs where each player gets at least their min-max value. WF is the payoffs themselves. So before it was the plays that give 0, 0 and 1, 1. So W is 0, 0 and 1, 1 themselves. And the set of equilibrium payoffs is the convex hull. Here closure is not relevant because we have 2 points, so it's not relevant, but generally it can be the convex hull of the closure of these 2 points. So here it's simply the segment connecting 0, 0 and 1, 1. Generally, it's the convex hull of the closure of these W epsilon F. So this is the Folk theorem that we get. More or less, this concludes what I wanted to say. So if anybody, I still have some time, but if anybody has any questions, now is a good time to say them, to ask them.
Galit?
Yeah.
Do you have any thoughts about whether this existence result can be generalized to stochastic games with limb soup payoff or tail-measurable payoff?
Yeah, Elon will tell you about them. I think yes, definitely, but I leave that to Elon.
Okay.
Yeah. Actually, I thought that you wanted to ask about, yes, I prepared this slide yesterday after your talk, that the regularity result, because you promised the crowd to have limb soup functions in my talk. So I added the slide with limb soup functions. So the regularity result is not just for sets, it's also for functions in the natural way. So that's another result that we generalize from 2 players to many players. Yes.
Thanks.
More questions? Okay. Then maybe we take an early break.
May I ask a simple question?
Sure.
I think when you explained the nice graph with the yellow part and the hash part, yes. So I think I understand why the white hashed part is not helpful to get an equilibrium, but the yellow part is slightly surprising for me because it's above the min-max.
Yeah.
And we still don't manage to get something.
Yeah, I agree. I heartfully agree that it's surprising. But then let's go again for this point here. It's 1/2, 1/2, or this 1/2 that, and it's very tempting because they get 1.5, 1.5. Better than any other equilibrium if we manage to get. It's very tempting to try and get it, but how can you get it? I mean, you have to play this with probability 1/2 and this with probability 1/2. So you have a randomization device, fine. The randomization device tells you this is the realization. This is what you have to play. If you're player 2, then you have a profitable deviation. You just found out that you're about to get -1. You can get more. You can get more. In a repeated game, we can divide the periods such that in a repeated game with per period payoffs, whether they are discounted or undiscounted, doesn't matter, limb soup, limit of the average, whatever. We can divide the period such that the realized play is going to be here. The realized payoff is going to be here. Here it's just the expected payoff. The realized payoff is either this or that, and none of them are individually rational. I think this is the source of the disappointment that we have here, that we can get only a small thing of what we're used to in Folk theorem. Yeah.
Galit.
Yeah.
So I like this very much. This result and work. If I had another life, I would do an intern with you on Banach Mazur. Instead of playing Gale or like playing one move at a time. So there are these Banach Mazur games where you can every player can be a finite number of moves, and then the alternate. And then you have determinacy beyond Borel. So there are set where they are not Borel and still you are determined. And this looks very compatible with the techniques they use, because there is always a player who fixes things for arbitrarily but finitely periods, and then you go. I mean, it could be that there you can relax this request to preserve length of the prefix that you replace. Because I mean, this gives a very nice sense of what happens in a repeated game if we take away what happens from in the fight. So we know how to analyze finite games. Yeah. Now let us look when everything happens in the tail, and it would be interesting if you could detangle an arbitrary payoff function to say this is something that matters for the finite part. This is something that is tail heavy. This is in between, and all. So I think it would be. I mean, this gives a wonderful basis, but to understand like what happens between games finite duration where we know the duration, and what happens in the infinite, and we don't care about finite fixes of no matter what length. That would be.
It sounds interesting. Sounds interesting. Yeah.
I was not. I'm not sure if I understood the question. Is the question of what happens when the payoffs are not tail measurable, but kind of a mixture between a tail measurable and a continuous payoff? Is that the question?
Yes. Yeah. The question would be take an arbitrary like wing condition and try to decompose, try to understand this tail measurable part of it, and with I mean, and well, it's more like a conceptual question. It's not anything algorithmic. I mean.
So let me say one thing. In a case where payoffs are a function of a stream of payoffs, yes, like in some of the examples that have been given here, they are works that are kind of trying to break the payoff into the composition of the payoffs into two parts. One that depends on the tail, one that depends on the stage payoff.
Yeah.
In the case that you have monotonicity.
Yeah.
Because then you could use the kind of an Ilya-Yoshida theorem of a decomposition of a measure.
Okay.
So if you have additional axioms, yes. So under additional axioms, there are work that will give you a decomposition of the payoff into two payoffs.
Mm-hmm. So you have classes of payoff functions where you know how to decompose.
Correct. Yes.
Yeah, because I wouldn't know. I mean, I didn't understand the tool that you mentioned. I mean, I'm not.
Ilya-Yoshida theorem that speaks about the positive linear functional on L infinity.
Mm-hmm.
Yes. And given it a kind of a partition that it is a kind of an L1 functional plus a charge, where a charge means that it's a purely finitely additive measure, an extension of a purely non-additive measures to functions of L infinity.
Wow, this looks very interesting. Unfortunately, I have a topology guru. I will look at this.
But Avam, who used it in repeated games? What are the words?
There is one recent work of myself.
Oh.
Yeah. And there is Graciela Ciesliński from '96, when she talked about sustainable preferences. Yes. So she basically, in terms of various economic work, she wanted to look for payoff functions that are both a function of the present and a function of the distant future, which is the infinity, the tail. Because otherwise, if you think of global warming or other things, you have difficulties of maximizing. So there are, she has kind of characterization in the case of just basically just a translation of the Ilya Yoshida theorem, which I mentioned, and there is a recent work of mine that is, in addition, requiring some axioms of the time value of money, that if kind of an overtaking criteria, but not only in the tail, but everywhere.
Very interesting.
So then there is a characterization, and also some implication of what you could do with optimization with such functions.
Very interesting. Very interesting.
So may I ask a question?
Sure.
So so this is very interesting. The concept of equilibrium here is a bit, for me, it's like we have an infinite duration game, but the deviation that is considered can damage even if the deviation is done once, as the classical equilibrium. Do you think it would be, because as I understand in your proof, you rely on the fact that deviation happens once or finitely many times. I think that's the crux of some part of the proof. Yeah. So do you think if one expects that the concept of equilibrium here depend on deviation, a punishment of infinitely, like a not only a finite duration punishment, but a continuous punishment, yes. Would it change a lot? Is this concept even studied, or does it make sense? Or can you elaborate a bit? Or sorry, maybe I'm just a bit.
So you're asking about the concept of the punishment being eternal, being forever? Yeah, well, actually, the only way to change the payoff of a deviating player is to do something forever, right? Because nothing you do in a finite number of periods affects the payoffs of the players here. So indeed, we can, instead of punishing after deviation once, we can decide that we punish after 10 deviations of the same player. Because 10 deviations will also give him nothing, right? He also needs to deviate infinitely many times so that something will change. So this can be changed to, I believe, any finite number, but still the punishment itself, in order to be effective, I don't see a way to avoid the punishment lasting forever. I don't see a way to avoid it, because otherwise it will have simply no effect on the payoff of the player. Anything you do a finite number of times. Yes.
I remember actually a paper, I think it was by Ehud and Silvan, Ehud Lehrer and Silvan Soren, but I could be wrong, where what they do in the construction, I don't remember exactly the result, but I think it was called epsilon consistent equilibrium or something like this, that if there's a deviation, then punishment takes place, but only with some positive probability. So if the player deviates, then maybe the players make a joint lottery, and if the guy is lucky, with probability almost 1, he will be lucky maybe, then they forget about it. And with small probability, they will punish, but then they will punish forever. So it's not subgame perfect, but it has a little bit more, but this is the only thing I can think of. But to be honest, I don't recall that concept exactly, so I could be very much offline here. But I think it was called epsilon consistency. I don't know.
Thank you, Galit. Further questions? Okay, then Thank you again.